Coding till the dawn, C++ and Sun, System Level 101, operating systems done, far from where we started from, operating systems done.
Welcome to today's operating systems lecture. This will be the last regular lecture, and I've just seen that the chat is not properly shown here, but instead you see a different window. Now the chat is shown. Yes, now it works. Okay, today we have the topic of file systems, and file systems, I'll try to make this topic as exciting as the other topics, but of course file systems is a lot about how do I organize this blob of memory storage that I have, and how do I find stuff on this blob of memory storage. So let's start. You find the Menti link, the Menti code up here. The Menti link is also in the chat and down there in the description if you want to participate via the Menti. Just to start with the motivation, computers have memory, right? They have RAM, and usually when we work with data in RAM. But RAM is not enough, right? We need larger memories than the main memory, so we need to store data somewhere. Also, sometimes we want to have persistent storage. RAM also cannot deliver that. So we want to have some additional storage location. Also, if multiple processors want to share data offline, not while they are running, but while they are not running. The solution is, of course, to have some storage like a hard disk or a similar device where we can store data persistently. The information becomes persistent, so it doesn't depend any longer on processes or their lifetime. The administration, of course, is done by the operating system, and that's where you come in, because you might want to implement this in the operating system's practicals. Okay, I will just quickly check, because on my side this looks a bit laggy, but no, probably everything is fine. Okay, let's start with an overview. The main points, file systems are useful abstractions for this blob of memory, and there are some usage patterns that play a role here, and we also have to discuss file and directory layout. We will talk about these points today, and also important, the user's view. How does the user see the file system? You know this perspective already because you have been using the file system in the past for previous programming exercises, for instance. And the user usually does not want to see or know or understand the file system or the blob storage, but instead the user just wants everything to work, right? The user does not want to know all these details. The operating system has to hide that from the user. The user just wants to refer to data, for instance, with a file name. So we will need a naming scheme. So what does the user want? Users want that the data is safely stored, so they want reliability. And also, for instance, if the system crashes, if some application crashes, the data should still be stored somewhere. Also, the data has to survive longer than the program that created it, right? And finally, also, you want to have large capacities at low cost. You can't afford that many terabytes of RAM and high performance at the same time. So it's maybe a bit of a contradiction, low cost and high performance. And then, of course, named data, you want to use it in a convenient way, usability. Control sharing, you want to control who can access what. So these are all wishes by the users, and we have to somehow implement them. So we are using non-volatile storage here. So storage, if we put something there, it should stay there basically forever, or as long as the medium survives. RAM loses the contents whenever the system crashes or when there's a power failure. When you reset the system, the data is gone, basically. Non-volatile storage, such as hard disks, keep the data beyond crashes. So you have a persistent storage, also stable storage, because it's not so easy to get errors in there. For RAM, you know, there's error correcting codes, but for non-volatile storage, this should be all persistent, stable, and usually you also have a higher capacity and lower cost there at the cost of performance. The performance will, of course, be much lower than using RAM. Non-volatile storage is an abstraction on top of persistent storage, because you don't want to care about how things are actually stored. You just want them to be non-volatile. You don't want them to go missing at some point. For instance, this can be an abstraction on top of a magnetic disk. It can be on top of flash memory, for instance, with a USB thumb drive, or more recently also with SSDs, which got very popular over the past 20 years. Devices provide you with storage, and this storage survives the machine crashes. So this is basically a feature that we can use now as operating system developers. We provide this feature then to the user without doing much for that. And also we have a block level there. These devices usually work in blocks, which is convenient for us to use because the operating system works with pages, right? They give us large capacity at low cost, and also, they are mostly reliable, but with slow performance. Now the file system role is also an illusionist role. If you remember from the first and second lecture of operating systems, we talked about these different roles. The file system is also the illusionist role, because you want to create this illusion that everything is unlimited, everything works perfectly fine, and it hides the limitations of the actual physical system behind that. So the persistence of data is guaranteed, even if a crash happens during an update, even if a block becomes corrupted, even if the flash memory is not writable anymore because it's too old, or if the writing doesn't work correctly anymore. The naming, you want to have named data, as I said, and directories instead of flat storage. You don't want to work with this data blob. Still, you want to, inside a file, address data byte-wise and not with some block metric, or thinking about how to work with a very specific disk device. You want to work very similar to with files, very similarly to regular memory operations. Ideally with the system calls that you already know: open, read, write, close. So the file system as the illusionist. Also, you want to create the illusion that this storage medium is actually fast. So you want to create the illusion of performance. And how do we do that? With the same trick that we've used before for the slow page table walks. We cache it. We cache it in DRAM automatically, and that's what we call the page cache. Also, when you actually store the data on the disk, you have to take care about the placement. Where do you place it on the disk? Is it expensive to move from this location to another when reading this, in sequential accesses, for instance? Also, where do you place the metadata? Where do you place the data structures? How are the data structures organized? Is this fast to work with for the operating system and for the hardware? And also that you somehow would control access to shared data, because in the end, if someone can write to the disk, they can write to any location on the disk. So the operating system has to take over this part to create this illusion that this would be controlled, and that there would exists some form of isolation on the disk, although it doesn't exist. It only exists in the operating system. Before we go into some design decisions and requirements analysis, maybe talk about some vocabulary that we need for that. And the first part is the file system. The file system is the operating system level abstraction that provides you with all these illusions, this persistence, the named data, the hierarchical organization, for instance, in folders, and access control. That the data is persistent, so we talk about persistent data, is stored until it's explicitly deleted, never gone unless we delete it. Named data, we can access things via human readable identifiers, passes file names, and then files, of course, where we can store some data in a sequence and access it byte by byte, so that we don't have to search on the disk for the right elements that belong to the same set of data. Metadata, for instance, information such as the size, the owner, security information about the file. What am I allowed to do with the file? Am I allowed to execute it? Am I allowed to read it? File data, the data in the file that we want to put there. We have different storage devices today. Traditionally, mostly disks were these magnetic disks, and they were rather slow, but also very large at the time. And the storage, these disks rarely become corrupted. This doesn't happen too often. So you get a large capacity, low cost, it's mostly reliable, and you can work on a block level where reading from the disk would read an entire block of data, writing to the disk, you write an entire block of data, and you get random access for these blocks. You can access any block that you want to access. The performance is slow for random accesses, but the performance is okay for streaming accesses, for sequential accesses. So now it matters how you place the data on the disk, because for the one case it's slow, and for the other it's fast, comparably fast. It's still much, much slower than DRAM. For more recent disks, for instance these SSDs, you use flash memory, and flash memory also rarely becomes corrupted. The capacity is, in principle it's lower at the same cost. This figure of 50 times disk is not correct anymore. By now you get the margin between those is much lower, but it's still more expensive than traditional disk storage. You also have block level random access, and it has good performance for reads. It has not so good performance for writes, for random writes, and therefore you have to optimize for different metrics here. Let's talk about types of files, because this is something that you already know. Files, and you know these files might have extensions, and even without the extension they might have a file type. For instance, let's talk about a text file, regular files, text files in ASCII or maybe UTF-8. You can have different encodings there. You could have binary files, usually with some internal structure, with some information about how this is structured, maybe a file header that tells you what type of file it is, but also directories as types of files. We will talk about that. And then maybe special files in /dev/proc that are not actually files, but that somehow still are placed in the file system on the operating system level, and where the operating system will provide you with data when you read from these special files. Okay, when accessing data, we are actually simulating much older devices, right? We are reading byte by byte sequentially, like in these old tape drives. We emulate a tape drive basically with sequential access, reading one byte after the other, and at the end we can wind back with, let's say, lseek, for instance. So this pretty much simulates this tape drive model. But with the introduction of floppy disks and then later on the magnetic disks, you have basically any sequence possible. You can access it in any sequence. You don't have to read everything sequentially. So this brings the random access capability. And this is also then where a seek system call is really nice to not just rewind the tape all at once, but where you can actually jump to a different location without a significant cost. File systems have different workloads, right, depending on the use case. And we definitely also, when we design a file system, we have to take the workload into account. How is the workload, or on what does the workload depend? Let's talk, for instance, about file sizes. We can have very large files or very small files. So what if most files are very small or very large? If they are small, for instance, we might want to optimize for a different amount of metadata. We might want to keep metadata smaller because we have more files, so more metadata, more overhead. If accessing files if reading from one file is fast and switching between files is slow, then also this would be a problem. If we take a look at our system, you can also take a look at your system and check out how large files are on average. You will find that most files are pretty small. So the question then is, if most files are small, what is responsible for the largest amount of occupied space on your disk? The large files, of course, because the distribution is a bit skewed. You have a few very large files and many very, very small files. So file system workload. What about file accesses? Are most accesses to small files or to large files? I would say mostly to small files, many small configuration files, many small scripts that are used, many small files that we're using all the time. But then the other question is, if we take a look at the input-output traffic, the disk traffic, which amounts for more input-output traffic, small files or large files? Then it's of course the large files again. So we want to optimize here that for file accesses, for small files, frequent accesses, and large files, long burst memory operations. How are the files used? Most files are read or written sequentially, right? But some files are read or written randomly at random offsets. For instance, database files, swap files. Some files have a predefined size at creation, and some files might grow over time. They might start at offset or at size 0, for instance, a log file, and then it will grow over time. How does the file system organize that? It's one big blob of memory. So you will have a similar situation as for the heap, where you also have one blob of memory and you have to also solve similar challenges. For instance, system logs, for this one. So we have to design a file system that for small files allows to store these small blocks on the storage efficiently. We want to have many concurrent operations and they should be efficient, more efficient than sequential. We want to put files that are used together, stored in proximity, because this can have an advantage on older disk devices. For large files, we want to store the file efficiently in large blocks, not in small blocks. And also we want to have some contiguency for sequential accesses. So if we have a very large file, it should be stored together on the disk in one location. And then, of course, if you want to access a random offset in a large file, it should still be efficient to find this random offset. So if you then have to go searching and it takes a long time, then of course this will not be so nice. Yeah, what do you say? Okay, let's continue with the file system design. So maybe we do not know at the file creation whether the file will become very large or whether it will stay very small. And we also will not know whether the file is persistent or whether it's temporary. Maybe you see that it's placed in /temp, but does that tell you much? Can you rely on this being temporary? So the question then is also, is it stored or written to sequentially, or is it written to at random offsets? We also will not know that. So we have to design a file system without knowing basically anything about these files and how they will be used. I think the cat wants to go out. Yes. So let's talk about file system abstractions, because we need these abstractions to actually work with this blob storage. And this should be a bit more convenient than just malloc and free, because as you may have noticed in, for instance, in ESP or OOP1, just having new and delete or malloc and free does not really contribute to organizing these small buffers inside the heap. There can be quite some chaos, and you might not know what is placed where and how to find the right memory object that you're looking for. So you will need some abstraction, especially for files, as this is persistent, this lives much longer, there's less context because you just place it on the disk, right? In the heap, this would be in your process context, so you at least can restrict it somehow that it belongs to this process. For the file system, this all doesn't exist. So for the file system, we need to introduce things like directories. Directories that group together named files or subdirectories. This can be a tree. And then you map from file name to some metadata location. So we only need to know this file name refers to this metadata here on the disk. This would probably be some kind of map. The path usually identifies the file and or directory or both, right? And then we can find the right metadata file. For instance, this could be a path to identify some operating system's file or folder. We also have the abstraction of a link in file systems. Hard links, where you link one name to a metadata location, and soft links, where you link from name to an alternative name. Also, we can mount file systems, so we map from name in one file system to the root of another file system. So we mount a file system into our file system. Let's go a bit more through the vocabulary here. Let's talk about vocabulary that we need to talk about file systems. The root directory, the root of the tree, if we have this hierarchical tree of directories, root directory would be the root directory of this tree. A path would be a string that identifies a file or directory. Absolute path, a path starting with /, so with the root directory. A relative path, that would be a path relative to the current working directory, another term that we need to define, the current working directory, the directory that the current process is currently working in, and it can change this current working directory. The home directory, some directory that is associated with the user if you have this in your operating system. And of course, when we now want to access files, we have to use these abstractions, these concepts in some form of API. So we want to create or delete files, for instance, with create and unlink. This is the POSIX. These are the POSIX functions for that. We might want to link files, creating a hard link. You might want to create directories, make dir, remove dir, open to open a file. So you tell the system I want to start accessing this file, and then close to say, okay, I'm done with accessing this file, I don't need it anymore. There are more system calls, of course. Reading from a file with read, writing to a file with write, you know these already. Searching for the right position, or placing the current, the pointer from where we read, placing that one at the right offset. Then if we want to force a write back to the disk, there's also an operation fsync, but there are many more, and these are just a few examples. On Unix, opening a file has many different uses, because in Unix or in Linux, everything is a file, right? So you open a file, you return a file descriptor, and then of course many things can happen. For instance, if the file doesn't exist, you return an error. This allows you to check whether the file exists. If the file doesn't exist, you can tell the open system call that it should create and open the file. If the file doesn't exist, if the file does exist, you can also make it return an error if you don't want it to be opened. If you just wanted to check whether it exists, you can let it return an error here. If the file exists but isn't empty, then you can zero it and then open. If the file exists but isn't empty, you can return an error, and so on. There are many options that you can all specify in the POSIX compliant open function. And this is the start of working with files and folders. So when talking about file system design, we have to think about small files and large files, as I said before. For small files, you want to have these small blocks. Already said that, but still they should be grouped together. For large files, we want to have the contiguous allocation, right? Yes, and we don't know what it is like at creation. The data structures that we need for that are, for instance, directories that map a file name to file metadata. So what we can do here is, inside a directory, right, because we have this map and we need to store it somewhere, we can store these directories also as files, just storing this information. In a very simple design, you could just write it into a text file. Here is the file name, here is where the metadata is. Place this on the disk, and this is your directory. The file metadata tells us how to find the data blocks, because the data might be split up over the memory. As you know, this is one big blob of memory, and if we don't know whether the file will grow, we can't make sure that it's always contiguous, because something might already be placed next to it. So we will have multiple data blocks to find. Also, when designing a file system, you have to design something like a free map or a usage map. You will also have this part in the second assignment for swapping, where you also maintain a map or a list or a bitmap to mark which disk blocks are free and which are not free. How do we organize these? Good question. Also, the device might have non-uniform performance, so some storage locations might be better than others, especially for old magnetic disks. This was the case. But also for flash storage, you might observe this. So the design challenges. So we now need to design a file system and need to think about how we can find files efficiently, and then how we are able to open them and find the right data when we read from it. For that, we will create maybe an index structure that tells us where the blocks of a file are. The index granularity determines the block size. So what is the minimum size of a block that we can store on the disk? And also the free space. How do we find unused blocks on the disk? For instance, by maintaining a bitmap, as we just said. This would be a simple solution to that. The principle of locality also plays a role here again. How do we preserve the spatial locality? If we are in one file, how do we make sure that it's still in spatial proximity on the disk? Reliability. What if the system crashes while the file system is changing something on the disk? So these are many different things that we have to consider, and different file systems have different approaches for that. For the index structure, for the granularity, for free space allocation, and for the locality. We will go through these file systems in more detail later on in the presentation today. And just to give you a short overview, for instance, for the old FAT32, FAT16 file systems, the index was just a linked list. You had some block size. You stored the information which parts are free and which are used in array, and the locality, well, you didn't care too much about it, right? You just got some block, and if next to your file there was no free space anymore, then you had to defragment the disk from time to time. So you would basically then copy data from here to make this location free and place data from the same file there to group a file together on the disk. And this defragmentation, you would run this from time to time to make sure that the system is actually running fast. More recent file systems have different solutions, but we will talk about them in more detail. Let's talk about the file structure. So the internal file structure, of course, is one thing, but what about the file structure that the operating system has to consider here? Does it matter? Does it matter to the operating system whether it's a JPEG file or a PNG file? It's just a byte stream. The operating system doesn't care whether it's a text file or a PNG or something else. On some systems, this is not necessarily correct, because the operating system there might perform more things, more operations. Also, even on Windows, the type can make a difference, but usually not for the file system directly. The file system will still just store the data on the disk. How do we implement this? How do we implement an operating system file system? Well, typically you would implement this as a tree of directories, an index structure, for each directory maybe an index structure. You would maintain these maps for free blocks. You would somehow decide where to put things based on some locality heuristics. And yeah, of course, there are a lot more implementation details. And we will go through a few example file systems later on today. How do we find named data? We started with a file name, right? And the file name, or the path, is first split into directory and file name. And once we find the directory, we can, in the directory, search the right file in there. And through some index structure, we then find the right storage block that we want to access. As we said before, directories are files, so you can imagine it pretty much like this. So you would have a name, for instance, the file music might have this number. So you have a file name to file number mapping. And then from that, from this file number, you can go into the index and check where the blocks for this file number are. Directories, how do we find a file in the directory tree? Well, we first search for the root directory. For instance, this could be a fixed file number, or maybe some constant in the operating system. Then we recursively go through the directories And we can actually also speed this up a bit by caching, for instance, directories as files. We can cache them. This is again principle of locality. So for instance, if we look up this file here, then we can see that we start with file 2, then we go into this folder, we check out the next file number, open this file, file 158, which is /home, then we check out the next file and the next file until we have found the file with the data that we wanted to access. This is a very simple form of abstracting the data storage from the file name, or introducing a file name abstraction into a file system. But of course, we could use open read write close for that, to modify directories, but maybe this is not too convenient. Maybe also this has to be separated, because otherwise we might have some side effects that we don't want. We don't want the user to know the structure of the directory, right? What if the user writes something there that is not valid? So the user could corrupt the directory. So maybe we don't even want to allow this. So the operating system should have control over the file numbers and what is written there. So we still can use open and create, maybe, but we want to have special system calls for other directory operations. For instance, to get the directory entries, special library functions for operating for directories, reading directories. Yeah, the directory is stored as a file, as I said. The file name, yeah, we perform a linear search through the directory for that, and that's fine for small directories, but for large directories, this can be really inconvenient. So what do we do for large directories? We can introduce, instead of this linked list where we search element by element for the right file name, we can also introduce a tree and sort this tree somehow and find the right file through this tree. If you have very large directories, then you might also have multiple of these tree nodes. Okay. Linking together files also becomes possible with that, because of course you can have multiple names now. You can just, in multiple directories, place the same number there in the folder, right? Just use the same number. Or if you want to perform a soft link, then you can just place a name and another name in this directory, and that would be a soft link. And then the operating system, of course, has to do some extra work, but yeah, that's how they work. So a hard link, you can imagine it like this. So we have here food.txt and bar.txt, and they just map to the same file number, and then you find the same file. That's how you enable links. Soft links, you would have some mapping to another file name, and the operating system would have to go and now say, oh, this is a soft link, I have to start with this one again now and continue searching. So how do we now, we now know what the file is, and we know how to find the metadata for a file with some number. How do we find the right block that belongs to a file now? And this is where we said we want to map from this file number to a set of blocks that are stored on the disk. Also, there are some other goals. We want to maximize the sequential throughput, and for that we have to place the data sequentially also on the disk. So this is one design goal. For random access, of course, any block should be accessible, and that in an efficient way. And also for small files, it should be efficient. We shouldn't have too much overhead, but large files should also not use very tiny blocks where you have to check this data structure again and again and again. So you want to provide an implementation where you basically provide all of these features. efficient for small files, but also scalable for large files. And of course, some place to store metadata. You will have to store some metadata. And we will go now through some case studies to basically take these design goals and check how different file systems implement them. We will talk about different examples here. FAT, the Unix fast file system, then NTFS, and then copy and write file system, or ZFS. And of course, following up on the Unix fast file system, we will also talk about X2, X3, X4. We will start with FAT. That's a very simple file system from Microsoft. It was implemented in the late 70s, and it was the main file system for MS-DOS and later also for Windows. There are many enhancements since the late 70s. For instance, if you take a look at FAT32, that allows to have 2 to the 28 blocks and 2 to the 32 minus 1 bytes of data. And it's still in use today on SD cards, sometimes on USB sticks. If they don't exceed 4 gigabytes of memory, then this is an option to use. You will also find that extended variants of this are still in use. For instance, the exFAT file format. The FAT file format basically works with a file allocation table, and that tells us where you find the files. For instance, here in this example, you can see file 9 and file 12, and you can see how these are placed on the disk. And the file allocation table will tell you to which file, which block belongs and which block it is. With FAT32, file allocation table, it's an array of 32-bit entries, and we have a reserved area of the volume used for this file allocation table, so you have some overhead for that. Depending on the size, the block size that you can configure to some extent, so you can choose from some different values, you have more or less overhead. But on the other side, if you work with very small files and choose a very large block size, then you might have the problem of internal, not necessarily fragmentation, but you don't use the memory, so some form of internal fragmentation. The file will be a linked list of FAT entries, and then you just go, when you go through the file, you go through this linked list and say, okay, next part is this FAT entry. So you would have a linked list that goes through this table here. Until we are at the end of file, for instance. There's one entry for each block in the volume, so you have constant overhead, or not constant, but linear in the size of the volume. The file number will be the index of the first entry in the file allocation table. This is also unique because there can only be one file at any offset in the file allocation table. For tracking free space, this is super nice, because if you look up the file allocation table and it says 0, then the block is free. Finding a free block, you can just search through the file allocation table. This is pretty much like in assignment 2, the inverted page table, or in assignment 1, the copy on write reference count table, where you also can search whether a page is in use or not based on the reference count. So you can just search through the file allocation table, or also the page manager page use table. You can allocate a block on the disk by setting this entry to use. Basically fill this with the next element for the linked list. But this can fragment the file system, because it could be in between two blocks that belong to a different file already. And then you have to run defragmentation to basically linearize this entire thing and to put data together that belongs together. FAT is widely used. It was more widely used a few years ago, but there's wide support for FAT. Most operating systems support that. It has poor locality with the fragmented files. For random access, it's super bad because you need to run through the file allocation table, through the linked lists. For metadata and access control, it's also limited because you can't store too much in these few bits that you have available. And also it doesn't support any hard links, right? Because you cannot provide any duplicate number here. The volume size and file size is also limited. As I said, 22 to 28 blocks. The block size can be up to 256 kilobytes, but then again, you get internal fragmentation. If you choose a very small block size, then you get external fragmentation. So you have fragmented files then. So also there are no reliability techniques that you have on more modern file systems. So it has a lot of drawbacks, but it's widely supported. And exFAT is still widely used. If you take USB sticks, for instance, they still today use very often exFAT for compatibility reasons. Let's talk about the next file system, the Unix fast file system. And that was released in the mid-80s, and it was very similar to the original file system in Unix. And it used a tree-based multi-level index. You had locality heuristics so that you don't have to defragment the system all the time. And today we still use X2, X3 that are based on the fast file system. And X4, of course. So how does this work? You have again some disk here. These are maybe different disk partitions. And if we take a look at one of these disk partitions, then you have some boot block, some super block. Okay, we will talk about that. Free space management, inodes, a root directory here, and then files and directories after that. So there's some format for the partition, and this is all placed on the disk. So how is this implemented? The boot block contains the bootloader, and this allows you to run some code there to boot the system. The super block contains information on the file system, for instance, the size of the partition, the block size, the pointer to the free block list, right? Because this could change depending on the volume size or the size of the boot block. Then we have numberings for of the root directory. We have some magic number to identify the file system type. This is also important for the file system. Otherwise, you couldn't recognize which file system it is, and a lot of other information in this super block. You can take a look at the super block in SWEP. SWEP doesn't implement this file system, but it implements the Minix file system. But the Minix file system also uses super blocks and inodes. So you will find very similar design there. The inodes, index nodes, these are nodes, and this is basically a one-to-one relation between files and these inodes. So one file is represented by one inode, and then you have data blocks somewhere on the disk that store the actual data. So you can imagine it pretty much like this. You have some inode array, and within this inode you get some metadata, and then you get pointers to the data blocks. There are direct pointers, but there are also indirect pointers, and these pointers would then forward you to other blocks to allow even more hierarchical usage of the memory block storage. Okay, how do these inodes work? We maybe have some file descriptor table here, and this file descriptor table has some information on what we can do with the files. And basically, these file descriptors contain pointers to inodes, and the inodes they contain all the information about this file and how it's currently used. And then in there you have these links to the actual data blocks on the disk. Let's talk a bit more about the inodes. What kinds of attributes are stored in the inodes? The file type, for instance, whether it's a directory, whether it's a file, whether it's a special file, and whether there's some file owner user group. Of course, you have to set this. So there is, of course, one, but which is it? So this is stored in the inode. Then you have some temporal information, for instance, when was the file created, when was it last modified, last accessed, the size of the file in bytes and blocks, the mode in which it is opened, so permissions, read, write, execute, and what you don't find in there, and you can see this also in SWEP, there's no file name in there. So the file name already doesn't exist here anymore. The inode is already after this mapping from file name to some numerical representation. What you would find in this, we are still talking about the Unix fast file system. You would find a bunch of direct block pointers there, and this is sufficient for small files. And then why do we have these indirect blocks? Well, to point to a list of block numbers, basically. Double indirect, to point to a block containing a list of block numbers. And each of these block numbers points to a block containing a list of block numbers. And then triple indirect, again, the same, but more hierarchy. And this allows you to reference larger files. And this is very nice because now we have some direct block pointers. This is great for small files. For larger files, it gets slower, but you can still get very, very large files through this indirect structure. So for a small file, it might look like this. And for a larger file, as I've shown before, you would have a hierarchy with more data blocks in use. So you have some overhead, you have some slowdown, but it's still possible. Very simple structure. With inodes, you can also support that files can have multiple names. You can just have directories that contain the names. And I think we are back. I think I just had a small internet hiccup, so I think it should be working again. I will also check whether the chat still works. Yeah, I think it still works. So if you type something there, I will also see it. Yeah, files can have multiple names, and you just place them in the directories. You put the numbers there, and then an inode is referenced multiple times. Totally fine. You can definitely do that. And that would be a hard link then. Let me just select a different window here to not, yeah, this is better. This would be a hard link then, and the inode can even contain the link count, so it can count how often is it referenced. And you know how, whether an inode is still needed or whether you can delete it. This is really nice. If the count is 0, then there doesn't exist any further reference to this in the file system, and that means that the file can be deleted. The number of inodes is limited. For instance, the file system might be full because there's no more free inodes. So you have to make sure that you don't create too many inodes. And the file system design, but we're talking about the Unix fast file system here, is limited in that sense. If all blocks are used, then you cannot create further inodes. Sparse files are also enabled by this basic design, because now you can create a file which is largely empty. Empty space does not need to consume disk space, and you can just create a large file, seek to a position very far at the end, write something there, but the rest doesn't really need to be allocated. And this should create a file of the size of 1 GB using one block. And it doesn't work like this on my ext4 because maybe sparsity is not supported in that case, but also you have to take care that this is still possible with the block size. For instance, with the Unix fast file system, the block size, of course, is limited. So if you have a sparse file, then you would have some inode where the direct pointers are actually not used, but maybe this inode pointer is used, and then you would have some data used here and some data used here. How do we place the data? Well, you probably want to place this in a way that it's very efficient. So you want to optimize for concurrent access to the data, to the metadata, and also to other files in the same directory. And depending on your disk, whether the disk is faster or slower or has to move around a lot to perform these accesses, putting them in spatial proximity can speed up things. Okay. In general, you want to keep the metadata close to the data, and directory and files that belong to the same block group you will also put together on the disk. So how do you place blocks on the disk? You want to optimize concurrent access, as we just said, to the data blocks, to the metadata, to different files from the same directory. And different directories could be very far from each other. This would be totally fine because that's not local anymore. And the principle of locality doesn't say that two different directories should be placed near each other. So what you do is you divide the disk into block groups, and then you distribute the metadata in between the files. So you put the metadata close to the data, and the directory and the files that belong together, place them in the same block group if possible. That means if you access files from one directory, you will get some spatial locality for the files in this directory. A new subdirectory might go into a different block group, but all things in the same block group will, if you access them in temporal proximity, then you will also get the advantage here of the spatial proximity in terms of performance. Of course, if you would put the new subdirectory always into the same block group, you would never place anything into a different block group. Okay, yeah, so basically you place these data blocks into one of these block groups, and their common approach is to just use a first free algorithm inside the block group. Here's some example. So we have a block group here, and you can see whether they are in use or not. And if we write to some file, we might use these two blocks here. So we fill this up, and yeah, if we write more, the more we write, the more blocks we fill up. If we delete something, of course, then we will create holes like this one. We can also reserve space, and this can be helpful if we want to optimize something. When the disk is almost full, then we can't do anything. For instance, if only a very few kilobytes are free, then the files will be scattered all across, because the first fitting block or block group will be used. But the Unix fast file system reserves some part of the disk, and it shows you a reduced disk size to the application so that it can actually do that more efficiently. When the free space is less than the reserved space, then the disk is considered full, even though it is not full. But the admin can still log in and free space, because this is still possible with the reserved space. Some operations are then still allowed. Let's go for the next file system. We talked about FAT so far and the Unix fast file system. Let's talk about NTFS. Windows moved after FAT to NTFS, and NTFS is Microsoft's new technology file system. It was released in 1993 and it has many features compared to FAT. New index structures, flexible metadata, improved security, improved reliability, and even it supports some form of links. It's still today in use as the primary file system for Windows. On Windows 10 you will find that some new variant of NTFS is still used. Index structures. NTFS uses the concept of extents here. And extents are variable sized regions of a file stored in a contiguous region on a storage device. This is really nice because this means that we don't have to use a fixed size block, but we can have a variable sized, not really block, but a variable sized region. And this has the advantage of requiring less metadata also and being able to find the locations faster. You also have a table, the flexible tree and master file table, to find the blocks or the extents for a file. So if you have a small number of extents, then you have a very shallow tree. If the file is badly fragmented, then the tree will be deeper. The root is also stored in an MFT, and this is similar to the inode array that we've seen before. And there we have an array of 1 kilobyte of MFT records, and then this gets fragmented more and more. The root contains a sequence of variable size attribute records as well. And they can contain data, metadata. The data is an attribute of the file system, and metadata also. Some metadata that is stored there. So how can we imagine what this looks like? We have the MFT here, and it contains these data attributes that we can see here. File name, the data, some information on properties of this file, whether this record is free or not. And then of course the data here, these are actually then links to the extents, as I've said before. And this is just a sequence. And if we need more than just these extents, then we will have a tree structure there. Yeah, the MFT contains the non-resident data attributes. So it's sequence of extent pointers. That means that we have these pointers at runtime in memory. And we specify the starting block and the length of the block as an extent, and the extents have variable size, so they can be multiple gigabytes, and this is very nice if you want to store both very small files and very large files. If the file is very small, then the attribute might already contain data, right? Then you don't need this at all. But if the file is very large, then this will reference, again, a tree structure with the extents. Metadata, NTFS supports a lot of different metadata tags. Standard information is needed for all files. For instance, when was it created, modified access, the owner, the security specifier, whether it's read-only, whether it's hidden, whether it's a system file, file name, the file number of the parent directory, and you might have multiple file name attributes, and that would be then a hard link. An attribute list, additional attributes that are stored in MFT records. The first record in this list would then point to others. So again, if we have multiple MFT records, you can see that here, then the attribute list points to the second MFT record. And of course, if you grow files, you might have way more MFT records. And depending on the size, you will have different sizes and different number of MFT records. So for a small file, you might start with a single MFT record, but as it grows, it can be a larger number. Growing files. Growing files is actually quite tricky if you want to make this efficient, but NTFS chose an approach that works reasonably well. So if we start with a very small file, let's say a log file, it's very small, then you might place the data directly into the MFT record. But as the data grows, then you cannot fit this into this data attribute anymore. And then you will create a small number of extents, and these are tracked by a single non-resident data attribute. So you then start using this extent tree structure. If the file is large, then the extent pointers do not fit in a single MFT record anymore, and then you can either use multiple non-resident data attributes in multiple MFT records, or the alternative is you use an attribute list in the first MFT record, and this indicates which record tracks which range. So you have some sort of tree structure. For a huge file with extreme fragmentation, this can look quite ugly. So the file attribute list can be made non-resident here, and then you have some more space that you can use for that. Metadata files also exist. So we have metadata files. Basically, in NTFS, you would just place the metadata directly in the ordinary files. So you don't have any special regions for that, but you just place them next to all the other files. So file 5, the root directory, then file 6, the free space bitmap, bad block list, security and access control information, and then some other files, maybe master file table of contents, and then some other files, maybe ones that the user created. And this makes it easy to dynamically grow metadata. NTFS also uses locality heuristics, as I've said, and there it uses some form of best fit algorithm. So it will search for the smallest free region that can still fit the size of the block that should be allocated. Applications now have to indicate the expected file size for this to work. So if applications do that, then you can use this feature. The start of the volume is reserved for the MFT table to avoid fragmentation, but then of course afterwards you can place anything on the table, on the volume. Copy on write file systems. Let's talk about copy on write file systems. We saw the copy on write concept already in segmentation. We saw it in paging. Now why not also use this for file systems? Copy on write file systems never overwrite existing data or metadata. Instead, they just write new versions to new locations. And the example, for instance, would be appending a block to a file, and then the old file just exists as before, but in our overlay, the file was modified and extended. So how does this work? We update the free space image or free space bitmap. We update the inode in the inode array. We update the file's indirect block, and then we write the file's data block. And we have to keep this in memory because we don't want to modify the actual file system, the actual data on the disk. An example is appending a block to a file. So we first find some free space. We write to that. We have some new bitmap, some new inode, some new indirect blocks, some data block. And we write there. And that now exists in our memory. Yeah, so basically we have our old storage here, which contains all the old data, and then we add elements in there and we place that somewhere, but the old things still exist in the unmodified way. Why do we use a copy on write file system? Because small writes are expensive, and we then can give an advantage to small random writes over large sequential writes. Small writes are very expensive, especially in RAID disk setups. So then you get a better performance, because now that you have your copy on write overlay for this, the operating system can decide when to write this back, or if to write this back at all. The caching that happens there will still provide you with the read capability, and then you can combine the old and the new data while doing that. Yeah, buffering writes is limited because we also want to have the data on the disk, so there's some trade-off how long we want to keep things in memory without writing them back. Okay, why do we want to use copy on write file system? For instance, for flash storage, we don't want to write to the flash storage all the time. We maybe want to wait a bit to aggregate more information on this. For instance, if we want to erase a block, clear it, but then we only have a limited number of write erase cycles, so maybe we want to overwrite it directly when the user wants to write to it again. Also the flash drive internally can already use copy on write techniques to virtualize this, and internally it will not write to the flash disk unless it's actually useful and necessary. Okay, new data, when you create new data, this would, on a flash disk for instance, be placed in new blocks, and the old ones would just be marked as cleared, but not actually cleared. And yeah, this is maybe below the operating system's file system, but it uses the same principle here. It doesn't actually perform the operation, it just says, okay, yeah, I've done that. Let's solve them in the future. You can also implement some versioning here, for instance, to allow creating different versions of the file system, and you just need to store the most recent update. So this would be an update in place file system index structure. So you have some inode array, then you have some indirect blocks and data blocks again. And now if you want to run an update, you of course would directly modify the data blocks here. But if you introduce this copy on write mechanism, you actually would add some more layers here. So you have some inode array now, and the root inode slots gets on top of that. And now you would be able to reference different versions of this inode array, and this can just replace the corresponding data blocks in the inode array. So this is overlaying them somehow. Okay, with copy on write file system, we don't want to overwrite the inodes. Maybe we can make them somehow mobile. So maybe we can store them in a file rather than in an array. So we still need to find the root inode, but we can then take the remaining inodes and not place them in an array, but just find them at a location that the root inode provides us with. The root inode might still be at a fixed location, and the inodes should then be copy on write. Yeah. We don't want to risk losing the root inode during an update, because otherwise we can't find any location anymore. So for this one is fixed. Okay, what can you do there? You introduce a version number and a checksum into the inode, and you can increase this version number monotonically. And for file updates, you would update then the oldest slot. If you have a limited number of slots for different versions, then you would always update the oldest one, and you could then restore a few older versions of a file. When something crashes, then you can scan the slots and identify the newest slot with the correct checksum, and with that you get some reliability. Very nice. The content of the file system is still stored in some tree there's reference from the root inode. If you update a block, you will first write it and all the blocks that also belong to it to a new location, and then later on reference this in the inode array that is currently the most recent version. So the root inode slots would point to one of these inode files, indirect blocks. This points to an inode array, and this tells us what the most recent version, or it points us to the most recent version of this data block. Another file system that was also influential on subsequent file system designs was ZFS. That was a file system that was used by Sun Microsystems and later on Oracle. It was introduced in 2005 with OpenSolaris. It includes some protection against data corruption. It also supports very high storage mediums. You have efficient data compression in there, volume management, snapshots, copy on write. These features are all in there. You have continuous integrity checking, so automatically you check for integrity errors and also try to automatically repair them. It's open source, OpenZFS, and this pretty much uses a structure that is similar to what we had before. We have some root level array. This brings us to some directory node here, the root directory node, then some indirect blocks. This gets us to some directory node array, and this is a small file with the data directly in the directory node. And here in this case, we will go to the data blocks here and reference them there. Okay, we have these Uber blocks here. This is actually 256 blocks, and they are at a fixed storage location. So again, this could run out, but as we have a tree structure, we can scale this up pretty much. The root is the Uber block, 256 Uber blocks. Then we can rotate around for successive versions. And if we have to restart, we scan the array for the highest sequence number and correct checksum, pretty much as we said before for the copy on write file system. And the Uber block contains the pointer to the root dnode. The dnode is a basic metadata object in ZFS. It's similar to an inode or a MFT, and it's a file, or you could say it represents a file, and we have a variable depth tree of these dnodes. The root is a dnode, and the leaves are data blocks. The dnode has space for 3 block pointers, and the tree depth 0 would be the one that stores the file's data. 1 pointers are pointers to data blocks, and then 2 pointers that point to indirect blocks that then again point to data blocks, and then double indirect blocks, similar as before, up to a value of 6. The block sizes, we can range them from 512 bytes to 128 kilobytes, and this is specified in the dnode what the block size is. So it's not globally for the entire file system, but you can specify this for one of the dnodes. The block pointer will be a 128 byte data structure to find the right block. And we include fields for advanced features such as compression, copies on different devices, file system snapshots, checksums, etc. Okay, there's one question on Menti. Let me check. Okay. Let me check whether I can see this. So what exactly will be asked in the assignment interview concerning the exam? Just the address calculations we did in the lecture or something else? There will be theory questions. So you're talking about the exercise interview for assignment 1. There will be questions for theory questions around virtual memory. And I think everyone will have to do a computation of virtual to physical addresses. I think everyone will have to do that, but also the tutors will, of course, ask theory questions to see whether you understood what you have implemented in your assignment. So, of course, this will include more theory questions than just this one. And it's basically just to make sure that you understood what you submitted there as code. But this includes, theory questions. Checksums. Okay, so we talked about the things stored in these dnodes, and basically whenever we update something, we can basically then just refer to a new dnode and basically place the update here. And this one can still refer old dnode arrays as well, but also a new one, and this one contains the update. ZFS also has a space map. Of course, we need to know where data is stored, and ZFS is designed to work for extremely large storage systems, and the bitmaps grow linearly with capacity. So this is similar as for other file systems where you also have to maintain a bitmap, and this grows linearly with the capacity of the disk. Large bitmaps, of course, affect the memory requirements. If you have a very large disk, then you also need to be able to work with this bitmap, so you need more memory. Also, there's some time that you need to read these bitmaps, so of course this is some disadvantage, but caching can somewhat help here, but it's unpredictable when you can release this, when you can remove this from the cache. The space maps exist for each block group, and then allocation is restricted to a subset of block groups. The space maps are in memory, so you store in memory whether some block is available or not. And the free space is stored as an AVL tree of extents. This allows to find extents of the desired size efficiently, and you can search through them without any performance degradation. When you update the space map on the disk, then you append the update to a log, basically, and you bring the space map up to date when loading from the disk. ZFS also, as we've mentioned locality in the beginning, also considers locality. Copy on write file systems in general are designed to optimize the write performance, because we are grouping them together. We aren't writing immediately, but we are grouping writes together. But a lot of work just updates a single block. So how can this be made efficient then? We have two things here. One is sequential updates and the other is batched updates. And for sequential updates, we perform these sequential writes, and almost everything in ZFS can be moved around. So you can move these denodes around. And if you are able to group one update into a single write of sequential blocks on the disk, then you can perform this in a sequential write. Only the Uber block has to be placed somewhere else, because that was a separate block. And sequential writes can be much faster than random ones if you have a magnetic disk, for instance, but also for SSDs, it's still true. And this gives you excellent performance for writes, even though more metadata is written, because you can group this together sequentially. For the other operations, you can batch updates, but also for sequential updates, they can be batched together. And then you can write several, in this case, example, maybe seconds of updates together at the same time. So the updates to denodes and the indirect data nodes, etc., are amortized over many writes, because you don't have to do these updates all the time and these write operations all the time. You just do them from time to time. Updates to the Uber block, the dnode, root dnode, and the dnode arrays indirect block, also amortize over many writes, because you don't perform them immediately. Where do we want to write the data? Well, we choose a device, we choose a block group, we choose a block, and that works as follows. ZFS pools many devices into one pool. And then you use a round-robin algorithm to basically choose a device which you want to write through from this pool. Of course, this has a bias towards devices with a large number of free space, because you want to fill them up. And this also maintains good locality. 512 kilobytes are written on one device before moving to another. So if you write 512 kilobytes, then they will land on one device with high probability. Choosing a block group, that was the next step. Then ZFS divides them into hundreds of groups of sequential blocks, and then you choose the first block that was used most recently. You continued there. Unless it is too full or fragmented, then you will choose the next region. So basically what we do here is when we choose a block that is not in the same group that we just were working with, then we will perform a first fit allocation. So we will choose some block group where this block, or within the block group. So we will choose a memory location on the disk where our sequential data will fit. When it's almost full, then we will switch to best fit, not first fit. So the search then might take longer, but we can actually use the space better. Other file systems, and with that we get back to file systems that you might know, are the ext file systems. And ext file systems are well known for their journaling. BitLocker is also a concept that might be interesting, but I actually will skip this today, so we will not talk about BitLocker. But also, if you want to know more about file systems, you will be able to figure out more if you look up BitLocker online. On the OSDev wiki, of course, you also find a lot of information on file systems. This is also a good resource if you want to implement file systems in your SWEP. The ext file system generations are used on Linux. So originally this was cross development in Minix, and they are based on the Minix file system. It's a quite clean implementation, and they are usually limited by disk sizes and file names, and depending on the generation, more is allowed. You usually have a virtual file system layer there, and this virtual file system layer represents the file system in the memory. The virtual file system is an interface that allows you to use different file systems underneath. So you would have some user process, some syscall interface, the virtual file system here, and then some set of different actual file systems, and maybe a page cache below that buffers the raw data from the disk. And this would allow you to maintain different file systems at the same time. The original ext file system was an extension of the Minix file systems. It was the first implementation of VFS. We were limited to 2 gigabytes of disk size, 255 bytes of file names, and then it had many successors, ext2, ext3, very widely used already, and ext4 now on Linux. Let's talk about ext2. That was the first successor, and what changed from ext to ext2? Well, it integrated new ideas from other file systems, for instance, from the Unix file systems, from the Berkeley fast file system, and it was designed to be extensible. Until Linux kernel 2.6, this is already some years ago, the volume size was quite limited to 2 terabytes, and we by now have 2 terabyte disks. So this will not be supported anymore with ext2. And it uses some form of cylinder groups and then superblocks and inodes. Inodes, as we described before on one of the previous slides. The attributes in ext2 are, for instance, compressed, whether a file is compressed, secure, whether the blocks will be overwritten with zeros after the file is deleted or not. Rather not for performance, right? But for security, you might want to do that. Synchronized, whether data is written to the disk immediately or not, whether the file is in append mode, so whether the file will always be open in append mode, so to add more content to the end of the file. ext2 also allows fast symbolic links. We have some form of indirection there, some file that contains just the name of another file, and usually you can work with them as if it would be the original file. Normally, these are stored as data blocks on the disk. So this is just a normal file, regular file, as every other file as well. You also can have fast symlinks where the inode contains the file name. Links, this is that part about links. The new part for ext2, and this goes in the direction of journaling already, is the dirty state. After an operating system crash, you would get some recommendation to use FSCK. Sometimes it's even enforced to bring the file system back into a clean state. And also these checks should be performed regularly to check whether anything broke, even if it's clean. The performance of ext2 was actually already quite good. We had some read ahead mechanisms, so we would read more than one block when we read from the disk, and when accessing files sequentially, so we already read these pages into memory. When reading directories, you can already read files, block groups. You block inodes and data blocks again close to each other on the hard disk. So if the hard disk brings your performance from this locality, again, this is giving you an advantage. Pre-allocation of if you allocate blocks to a file, then you will get continuous or contiguous blocks on the disk to some extent. And also the read-write performance is then optimized because of these contiguency. Yeah, X2 also works with inodes, and when taking care of which locations on the disk are free or not, then there's this inode allocation bitmap and a data allocation bitmap, and by that you can determine which inodes are available and which data slots are available. There's a maximum file size, and this maximum file size depends on the block size, and there is a formula that you can use to compute the maximum file size. For instance, if you choose a block size of 1 kilobyte, the maximum file size is 16 gigabytes. If you choose a block size of 4 kilobytes, the maximum file size would be 2 terabytes. But this is X2. We move on to X3, which basically relaxes these limits a bit and really goes into this direction of journaling. And journaling is a concept that we will talk a bit more about. X3, yeah, basically it's a simple file system extending X2, and it's well tested, it's widely used. The differences to X2 is that it has a journal, that file systems can grow dynamically, and a hash tree for big directories to be able to find data faster. X3 uses a journal. A journal, in German you might know the word Tagebuch. A journal is pretty much like an Ingenieurs Tagebuch. So it's some thing where you go and write into what you are doing step by step. And the idea of this journal in file systems is that every change is stored into a journal. And this is sort of a cyclic log. And the first change, the first thing you do is you note the change in the journal, and then you execute this change in the file system. After that you would update the journal in some cases. In other cases, if it's recognizable that this change was executed, you don't even have to update it. Or if the journal can be re-executed, as in this design, after the crash, the operating system can just go through the journal and reapply these changes to the file system. Reperform these writes, reperform these renaming operations, relinking operations, whatever you changed. A typical scenario would be the file system is consistent, you request some changes, you note the changes in the journal, you execute them in the file system, and everything worked fine, and it's just like in a stable storage. But in other cases, this might go wrong. How does it work with journaling if you delete a file? Well, now you need two steps. You first remove the reference from the directory, delete the inode. What happens if you have a crash between those two steps? Remove the reference from the directory, delete the inode. Then you still have the inode. So what you need to do is you add one more step to this to avoid this orphaned inode, to avoid inconsistency. You can also not just change the order, because otherwise you have a deleted inode and the directory still references it. So what you do is you use a journal, and with this journal you would first write into the journal, then perform these two steps, and then when rebooting after a crash, the operating system can tell that this has to be performed again, and it will perform these steps again, and then the file system is consistent again. Without a journal, you would now have to do a file system check at reboot, but now we just read the entry from the journal, execute the changes if necessary, and the file system is consistent again. So we don't need to scan anything, we don't need to scan for orphaned inodes. But basically this introduces some form of atomicity, because either the changes have been done completely, or if they haven't, then we can still run them again after the crash, because they have not been completed before the crash. Yes, how do we implement journals? Well, we also put them on the storage. It's a regular file, it may grow, it's a hidden file and may not be moved, so that we can find this. Maybe it's a special area on the disk, maybe it's a separate device, and Maybe also we need a journal for the journal, right? So we want to be able to check the integrity of the journal as well. So some checksum would be nice. We want to ignore entries with incorrect checksums because maybe they have already been partially overwritten. And we now have to think about how we can use journals in an actual file system in the operating system. So as a first start, how do physical journals work? We write a copy of each block first into the journal, then on the disk. And upon a crash, we can either find whether it's neither in the journal nor on the disk, then we don't have to do anything. Or if it's only in the journal, then we copy it to the disk. Or if it's already on the disk, then we also don't do anything. This has a high overhead, of course, but it's acceptable if you have high correctness requirements. Much easier is a logical journal where we only write metadata into the journal. And this, of course, doesn't save as much, right? It saves you from the orphaned inode problem. It saves you maybe from some file creation and the file doesn't exist yet, but it doesn't save you from data loss entirely. The metadata journal may lead to asynchronicity between metadata and data, and if you, for instance, enlarge a file, for instance an inode, change the size, then you change the free space bitmap, then you get this new block from free space bitmap, fill it with data, and if you want to do that, you have to write that all into a journal. The logical journal only does not contain step 3 because this one is the data. And this will lead to a correct structure. So the tree structure, the file structure in your file system will be correct, but the file might contain garbage or zeros. So the journal, writes to the disk are optimized by the operating system as before. So the journal might be written after the changes to the disk are already committed, right? Because it could be buffered by the operating system. So what we want to do is we want to synchronize things here so that the journal is on the disk whenever a change is also on the disk. The journal must enforce flushing of the disk caches. In X3, we have 3 levels of journals. We have the first level, journal minimum risk taken. Data is written to the journal, data is then written to the disk, and then data has to be written twice. So this is the minimum risk approach. Then there is the ordered level, where a medium risk is taken, where only metadata is written to the journal. Then the data is directly written to the files. So this was the intermediate approach that we just mentioned. Then changes to metadata in this approach are only declared committed. So once you've done them, you mark them in the journal as done. They are resolved already. Only if data is involved, then there might be a step that you can skip. Okay. And of course, the third level, you don't have to use any journal at all if you don't need any protection. Write back, that's the highest risk taken. And that would be only metadata is placed in the journal. Data written to disk eventually just is placed on the disk. The data structure is safe in all levels, in all 3 levels, but there are no checksums on the journal. So the content is only safe in level 1. X4, and with that we are already very close to the end of the file system chapter. X4 is the successor of X3. Basically it just extends the existing mechanisms, so we blow up the volume size to 1 exabyte. and the file size to 16 TB bytes. So it's 2 to the 60 volume size, 2 to the 60 bytes, and 2 to the 40 bytes file size. So this is quite large and should be enough for some time in the future. It uses extends, it uses pre-allocation, it uses allocate on flush journals with checksums. So all of these features are used nowadays, and that's the file system that if you are using Linux right now, you are probably using right now. And with that, we are at the end of the operating systems lecture for this semester. Next week, we still have the assignment A2 tutorial, but other than that, we are done, and I'm still available for questions if you have questions. File systems is, I need to find a way to make this more interesting next semester. So maybe more focus on the design decision and less focus on the specifics of the different file systems. But of course, it's similar to, from my perspective, it's similar to driver development. File systems is basically a lot about organizing some memory, and as these file systems that we've talked about for half of the lecture already exists, it's basically understanding their designs rather than coming up with your own design. And for virtual memory, when we talked about that, we tried to come up with all of these ideas on our own, because all of these choices were pretty intuitive. Maybe with file systems, we can also get there with the lecture, but currently I'm not there yet to make this really intuitive, but in the future maybe. I don't see any questions on the Menti and also not in the YouTube chat, and that means that I will just thank you for your attention and see you next week for the presentation of assignment 2.